Hello, my name is Maxwell Hogan, and on behalf of my collaborators, I'd like to present our work on using convolutional neural networks for relative pose estimation of a non-cooperative spacecraft with thermal infrared imagery. I will start by giving some background into the challenge we are attempting to contribute to and the specific problem we are tackling in our study. I will then discuss our approach and the preliminary study which we had conducted using only synthetic data. Following that, I will then discuss our main study where we evaluated our network using real thermal images we had collected in a laboratory environment. And as part of this discussion, I will be showing how we use GradCam to get better insights into our network. Finally, I will discuss future work we wish to conduct. Non-cooperative rendezvous missions require a chaser spacecraft to determine the precise location and orientation of a target spacecraft without the assistance of that target spacecraft. This puts a heavy burden on the perception capabilities of the chaser craft, and any solution needs to be robust to the illumination conditions that can be faced on orbit. These include an eclipse where the target could be in complete darkness, or in contrast the target could be in full sunlight with the sun behind the target or behind the chaser. There could also be the situation where the lights could hit the target from the side, resulting in only a portion of the target being illuminated and other parts being in complete darkness. Moreover, any solution has to be self-contained on the chaser spacecraft with minimal support from the ground station. This is so that the chaser spacecraft can respond without delay during approach. The illustration shown here shows the geometric relationship between the chaser body, the camera frame, and the target body frame in the context of landmark imaging. This approach for monocular pose estimation involves matching 2D image features to the 3D model of the target. This utilizes image processing techniques to extract features that have been chosen by the designer. The drawback here is that the designer has to consider fringe cases. These can arise from dynamic lighting conditions in visible images, and in thermal, unique or unforeseen cases could arise due to history effects. This is the time it takes for temperature variations to propagate. Convolutional neural networks are gaining traction in the task of pose estimation for both space and terrestrial applications. This is due in part to the fact that features they extract are learned through optimization. When trained properly, the network should be able to generalize well and thus be more robust to fringe cases. Typically, CNNs for these applications have been targeted for use with visible sensors. The drawback here is visible cameras drop in reliability during low light conditions and are susceptible to oversaturation from sunlight. On the other hand, thermal cameras are less susceptible to illumination conditions that would otherwise hinder a visible camera. For instance, thermal cameras do not rely on external light sources, which makes it possible to observe the target even in complete darkness. Moreover, reflective surfaces on the target can cause a visible sensor to become oversaturated, while in the thermal, these surfaces should appear smoother. However, the thermal signature of a target is not often known prior to the mission and is quite difficult to investigate and then model. This is a major roadblock in the development of any algorithm, not just convolutional neural networks, that is intended to be embedded into an infrared camera feed. On the other hand, visible information of a target is much easier to acquire and in most cases we can assume is already available. Therefore, it is the motivation of this project to develop convolutional neural networks that have been trained exclusively on visible imagery of a target and then evaluate their robustness on thermal images of that target. We demonstrate this first on realistic synthetic data, and then we expand our study further by evaluating our model on real images of a replica spacecraft. In this project, our goal is to develop a coarse pose initializer which can be used to identify which facet of a target the chaser is observing. This information can be provided to a more precise algorithm to refine the pose estimation or be cross-referenced with other sensor feeds. We have used the concept of a view sphere to capture the full three-dimensional aspect of the target. This imagines a sphere around the target, the surface of which is covered with cameras pointing toward the target at the center. The image on the slide now shows the illustration of such, with one of our target spacecrafts, the JSON-1, at its center. Any viewpoint can be described using spherical coordinates of a camera on this sphere in terms of azimuth and elevation. The first stage of development used a synthetic dataset of the ENVISAT. This is a decommissioned oceanography satellite and is the target of ESA's ED-orbit mission. Further details in the paper are available, but to summarize, the dataset was generated by the ASTOS camera simulator, and it consists of photorealistic images of the ENVISAT in both visible and thermal infrared modalities. An example is shown here of the same frame in the visible above and the thermal below. The dataset is organized into sequences of images that simulate certain scenarios that might be faced by a chaser spacecraft as it approaches. It contains images from a V-bar approach with a deep space background, or an R-bar approach with the Earth in the background, such as the pair shown here. We trained two models based on ResNet 18 and ResNet 34 to classify the observed facet into one of 10 classes. For this stage, we limited the problem to 1 degree of freedom, so each class represents 36 degrees of rotation along the azimuth, and elevation is fixed to 0. The networks were trained exclusively on visible images, and our test set is composed entirely of thermal images. Seen here are the confusion matrices for both of our ResNet models. Both networks performed well on the task as indicated by these high scores across a diagonal. We also calculated the average precision and the average recall for both networks. And from these, we determined the average F1 score for each network. This is recorded in our paper. The F1 scores were 82% and 88% for ResNet 18 and ResNet 34 subsequently. The results indicate that the ResNet style architectures are robust to changes in the modality. However, the task here was relatively simple since we limited the problem to 1 degree of freedom. Moreover, with 10 classes representing a large set of viewpoints, we are not challenging it to make more precise angular predictions. Therefore, moving forward into our second stage, we expanded the problem to 2 degrees of freedom, and we also increased the number of classes so that each class will represent 10 degrees of facets. The second stage of our development was to train a network using only synthetic visible images, and then demonstrate that the network was robust on real thermal images. In order to do so, we created a 1:4 scale replica of JSON1, which we could use to capture a continuous sequence of images for our test set. This is shown here. The replica is mounted atop a motor that spins at 1 RPM, and you can see we capture both modalities simultaneously. This is so that we can compare the performance of our network on real visible images to the real thermal images. The CAD model of our replica was used to generate our synthetic dataset using the open source modeling software Blender. More information on this and our laboratory setup can be found in the paper. In this stage, we developed a single model based on ResNet 101. We replaced the final fully connected layer with 2 fully connected layers, with one to predict the azimuth class and the other to predict the elevation class. The results on our test sets are shown here. The horizontal axes represent the error in terms of bin distance, where a 0 represents a correct classification, and the vertical axes show the relative frequency. In addition to both the real thermal and real visible sets, we recreated the sequence of images in our Blender environment to compare. The model performed better on the task of classifying the elevation. As can be seen here, for all 3 conditions, the network was able to place 90% of the predicted elevation class within one bin. This corresponds to a maximum error of 20 degrees. On the other hand, for the task of classifying the azimuth, we found that the network was only able to place 60% of the synthetic set within one bin, and for both real sets, only 50% within one bin. Nevertheless, in all 3 conditions, 80% of the predictions were within 2 bins, which corresponds to a maximum error of 30 degrees. Moreover, we also calculated the absolute angular error between the ground truth and the prediction, which is a combination of the azimuth and elevation error. In order to do so, we calculated the vectors for both the ground truth azimuth and elevation values and the predicted azimuth and elevation values. You can imagine this vector as a line connecting the center of the camera to the center of the target. We could then use the equation shown here to calculate the error between these two vectors. Since we are not considering the camera's roll and our target is at a fixed distance and fixed within the frame, this value is essentially the attitude error. We found for all three conditions the mean error was below 20 degrees. From our results, we can see that the model performed best on the synthetic set, which is unsurprising since this set most closely matched the training set. This does indicate that there is still some difficulty moving from synthetic to real images. What is interesting is that the network achieved very similar mean and median scores for both our real sets. This indicates our network is almost robust on real thermal as it is on real visible. Moving forward, we wanted to investigate our model further. We wanted to know what it had learned about our target and what reasons might there be for its failure modes. This is something very important if we were to even consider deploying it in the wild. Due to their black box nature, deep neural networks are inherently difficult to trust, and this concern has driven an increased interest in explainable AI. In order to better understand how our model makes decisions, we have employed GradCam. This method can be used to generate a coarse localization map highlighting the important regions of the image. We refer to this as an attention map. Shown here is the image which was given to our network with the GradCam overlaid. The blue indicate areas of least importance, whilst the green to red indicate more important regions. I won't be going into full detail about how GradCam works. However, what is important is how you encode your target concept. This is to say, what aspect of your network's prediction you are trying to explain. In an ordinary classification problem, one would simply one-hot encode the target class. For our case, we one-hot encoded our prediction value for both azimuth and elevation and then summed them together. This would allow us to generate attention maps that show the features that were most important for both predictions. We found that throughout, the attention was focused on the central bus of the target. This makes logical sense since it is both the center of our target and also where many of the unique components are found that would otherwise be absent if we were looking at the target from a vastly different orientation. We also wanted to understand why our network had misclassified the azimuth prediction of some of our thermal images as 180 degrees out. You can see this contributed significantly to our network's error. We hypothesized that this mistake may be the result of the symmetrical nature of the target and wanted more information to support this. In order to investigate this error further, we generated the attention map for one of the offending frames, only taking into account the azimuth prediction and excluding the elevation prediction. This is done by simply one-hot encoding the azimuth prediction. This gives us an attention map that shows us the important regions that led to a given azimuth prediction. You can see that the focus now covers much more of the near solar panel. This supports our hypothesis, as the solar panels are a symmetrical part of the target which could cause some confusion. This is made more challenging in the thermal, as you can clearly see the support beam is showing up through our panels. Looking at the same frame now, but from the visible camera, we can see that the attention includes a substantial portion of both solar panels. In this case, you can see the below image that the network was able to find a close match for this frame. For many of the visible frames from this side of the target, we found that a lot of the network's attention was on the solar panels. This indicates to us that the patterns on our solar panels is important to the model. I now have the same frame in the visible and infrared shown here. From our investigation with GradCam, we can see that our network has a bias towards the solar panels, and since the pattern cannot be observed in the thermal, this puts it at a disadvantage. However, with this knowledge, we can remove this pattern from the training set to try and improve our performance in the future. Moving forward, using knowledge acquired with GradCam, we would like to refine our training set to maximize the performance on the thermal datasets. Currently, our experimental setup is limited. Therefore, we would like to improve upon it so we can evaluate different approaches and different illumination conditions. We would especially like to evaluate conditions where we'd expect visible cameras to struggle. Finally, we would like to investigate how well GradCam can localize the target within the frame. From this, we may be able to infer positional information about the target. I'd like to take a moment now to thank you all for listening. Once again, my name is Maxwell Hogan and my contact email is on the screen now. Feel free to get in touch if you have more questions or any other interests surrounding my work. Thank you.